Good morning, fellow mathematicians! Welcome back to another video! No yet again today, because today marks the start of a brand new series on this channel, namely on quadratic functions. Those are polynomial functions of just second degree. What this means we are going to talk about in a second. And if you want to learn more about quadratic functions, make sure to check out the link at the top of the description as well as the info box. You can find the whole playlist there, meaning there's everything in there that you are going to need for your whole school life and also the start of the university. So check it out, it's definitely worth it. As per usual, we are going to at first take a look at an overview of the playlist. What is going to be covered in here? What are we going to do overall? You can find the most important points that we are going to cover here in this video, and later you can check the playlist down there if the video is already in there. And if it is, have fun watching. And now we are going to dive right in. So I want to think back to linear functions that we have covered the last time around. Namely, linear functions were polynomial functions of the first degree. Meaning, we had f of x being equal to ax plus b. And why are they called polynomial functions of the first degree? I'll tell you why. Because the highest power of x that we are going to find here, the greatest exponent is going to be 1. Because x, or 3 or whatsoever, is nothing but 3 or x to the first power. Meaning, what we have here is a times x to the first power plus b. Meaning this right here is a polynomial of the first degree because the highest power of x is 1. Now we would like to expand this idea by dropping a 2 up here instead of a 1. And I want you guys to notice that each and every time we have an x, or maybe we don't have an x, we are going to put a certain coefficient on there, a and b. And now we need to expand our idea a tiny little bit. So we are going to put a 2 on here, then we are going to have ax squared plus, and now we are going to have b times x to the first power. And at the end, we also need some y-intercept, you could say. Okay, it's not really the y-intercept, but we are going to cover this later. Okay, plus c. So those right here are our general quadratic functions, also called parabolas. And yeah, we are going to take a look at those in this whole playlist. There's a bunch of stuff we are going to cover here, and we are going to start off with the easiest case, starting with the next video. Namely, it's just a normal parabola. It's just a function of the form f of x being equal to x squared. And we are going to notice that this is going to be the parabola, which is neither stretched nor squished nor reflected in any way. It's just a parabola looking like this, going through the coordinate system's origin. So this is what it's going to look like. F of x being equal to x squared. We're going to experiment a bit around, okay, using decimals and stuff like this. And then we are going to expand our horizon a tiny little bit. We are going to put a coefficient in front of our x, and we are going to say, okay, the next class of functions we are going to look at is f of x being equal to a times x squared. And then we are going to notice something really curious. Our normal parabola is going to turn into something weird. Namely, we can have parabolas of this kind. Okay, this thing right here is weird. It's kind of squished together, okay? From this fat guy to this really small guy. But we can also have really fat boys, okay? We can also have functions like this right here. Or we can get a bit more creative and get something like this. And those are functions which can happen by actually putting different values for a in front of our x squared. So that's going to be the next class of functions we are going to look at. But then we are going to expand our horizon a tiny little bit more. Just like with our linear functions, we were able to, well, shift them up and down on the y-axis. We can do the same for our f of x being equal to ax squared. But what we are going to do is we are going to drop our a yet again. And we are going to say, okay, we are going to take a look at just some function x squared plus c. Okay, basically what we are doing is we are going through many cases that we can have up here. So we can just cover this up, and then voila, x squared plus c is what we are going to be left with. And with this form of a parabola, we can actually have a normal parabola being shifted up and down in a coordinate system like this, or maybe like this, etc. So this is the next class we're going to take a look at. And we can't just shift it around on the y-axis. We can also shift quadratic functions, I'm sorry, on the x-axis, back and forth. So meaning we can have functions of this kind, or maybe functions of this kind, etc. Those are tiny little bit more fiddly squiddly, because to find out how to shift them around, we need to convert our quadratic functions into the so-called vertex form. This is one big thing we really need to take a look at. It's the so-called vertex form. It's one of the three forms our quadratic functions can take. It can have the generalized form, this is this one up here, then the vertex form. Vertex form is going to tell us where the highest or lowest point of the parabola, meaning here, here, or maybe here, is going to be exactly in the coordinate system. We can actually read from this form where our vertex is going to lie. It's extremely useful. And also there's the so-called factorized form. This factorized form will come into play once we find out how to actually calculate the zeros of or the roots of our quadratic functions. So before we get to the roots though, we need to cover something a little bit more difficult, you could say. Namely, we can take all those movements that we had, up and down, left and right, etc., and squishy and just stretchy, and we can actually put it into one formula. That's a generalized form, for example, and we can do all of those with those parabolas at once, meaning we can have a parabola which looks like this, for example, or we can have one which looks like this, or we are going to have one that looks like this, etc. So we can shift it around to each and every position in our coordinate system in some way. And to find out where the vertex is, we are going to convert it into the vertex form. After we are done with that, we need to do some casework, because with linear functions it was kind of easy. We were always able to find out the root of a linear function, or the zero. It always had one. If this right here is our x-axis, doesn't matter which linear function we had, it always passed through our x-axis in some way. But we don't have the same situation here with parabolas, because you might notice this parabola right here doesn't have a root. It just doesn't have one. It doesn't pass through the x-axis, not a real root. Okay, that's a tiny little bit of harder mathematics. Maybe we are going to cover this in an advanced episode later. But for example, this parabola here has exactly two roots lying here and there. But we can also have something like this. This parabola here has only one root, and it's exactly at the origin. And hence, to find out those roots, we need to get a bit creative. We need to discover, or we need to derive ourselves the so-called quadratic formula. It's just a formula helping us to solve functions of this kind for x, basically solving for the roots. We are going to derive the quadratic formula using what is called completing the square. This is something that we need to do. We are going to cover this extensively, and with this way we can turn this equation, for example, into the factorized form, and this is also going to make matters way easier overall. Other than that, we are going to take a look at a few specialized episodes. We are going to take a look at Vietas Formula for quadratic functions. We are going to integrate and differentiate a function of this sort, and yeah, that's basically it. Also, we are going to do practice sessions and maybe some specialized episodes in the game, like rotating a parabola in the coordinate system instead of shifting it around. Kind of interesting. Yeah, and that's basically it. So if you're looking for the videos, okay, you can find them down there in the description, in the playlist. That was just a tiny little bit of overview I want to give you before we get started. And I hope you did enjoy this video though, still, whatsoever. I thank you guys for watching. If you did enjoy this video, then subscribe and comment channel, like, don't forget to visit STEM merch for the kitty catties and also our brand new nonlinear dynamics and chaos collection. You can find the link down there too. Other than that, visit the main channel too, and up until the next video, I'm wishing you guys a flammable day. Ciao!